All right, calculus students and seekers of general truths, let us dive deeper and deeper into the truth about transcendental functions, and we'll begin here with tan inverse of x. So if you recall tan inverse, we are passing into this a ratio, and what comes out of it is an angle measure. Okay, so don't forget that we are passing in a ratio, a trig ratio, opposite over adjacent, or the y coordinate over the x coordinate, and we are getting out an angle, okay, in the unit circle. And we have relied very much on our calculators to do this work for us. And today, right now, we see a little bit of what's going on behind the scenes of all this wonderful calculator technological magic, right? So let's start with finding a series centered at x equals 0. Now, we've sort of built up to this point. If you recall, the antiderivative of this function, 1 plus x squared dx, is in fact equal to tan inverse of x plus a constant. Okay. But wait a minute, wait just a minute. We have a different way of writing this function here. Using our power series, we know that that function can be expressed as the following power series. Okay, so let's get down to the power series expansion of this. So the power series expansion for this power series here is 1 minus x squared plus x to the 4th minus x to the 6th, and so on, onwards to infinity. Okay? And this is all going to be equal to tan inverse. I'm not writing the constant because the constant is going to be the same for both of them. Okay? So, I'm sorry, it's going to be relatively, it's going to be negligible once we work out all of the details. You'll see in a minute. So this power series expansion is in fact equal to tangent inverse, and I should say this is the antiderivative of the power series expansion, right? So this power series right here, right, that expression right there, once we expand it, is equal to all of this. And then once we actually take the antiderivative, we will get x squared over 2 minus, I'm sorry, ooh, that was almost disastrous there. The antiderivative of 1 is x. The antiderivative of negative x squared is x cubed over 3. This antiderivative is x to the 5th over 5 minus x to the 7th over 7, and onwards to infinity. And again, I'm dropping the constant out here from our work. Okay, if we were doing a specific example, we have to look at a constant. And then what we can do now is compact all of this down if we want to, right? Just so that you see that the general term for all of this is going to be n equals 0 to infinity. Okay, and these are all the odd terms, so we're going to need to do this great trick of 2n plus 1. Right, so x is to the 2n plus 1. That will produce all of our odd terms for us. And then to get it to alternate, we do the negative 1 to the nth. And this expansion, or this power series here, let's see if it meets our requirements. Well, it is a power series. This is a constant here, and then this is x, and it's centered at 0, right? Because you can think of this x here as like x minus 0 to the 2n plus 1. Okay. And this says something quite amazing, namely that this polynomial here on the left of this expression is equal to the tan inverse, or at least if we were to keep on expanding this onwards and onwards, we could use this polynomial to approximate the result of tan inverse. All right. So let's see what we've done here. Series centered at 0. It approximates, right? So I'm saying This is an approximation. It may not exactly be the perfectly exact answer. Okay. Now the next part is we need to determine values of x where the series will converge, where the series converges. And so this is a little bit new because for all of our convergence work we've done so far, all we've really done is use something that has a specific number for x. And now we're going to try to figure out a general case for this. All right, so to find the values for which this series will converge, right? So if the series doesn't converge, it's not much use to us because we plug in a number for tan inverse of that, a number for tan inverse, and we get infinity. So that might not be entirely useful for us. So to find the convergence here, we could use the ratio test. Right? The ratio test works out pretty nicely here. So the ratio test is the limit as n approaches infinity, right? If the limit as n approaches infinity of the absolute value of a sub n plus 1 in a series over a sub n is strictly less than 1, right? If this is true, then the series then you have absolute convergence. So what values of x? Well, let's test this out. This is the limit as n approaches infinity. The a sub nth term here would be x to the 2n plus 2 because we're substituting n plus 1 into here. And actually, I don't want to skip over that step too quickly. So this is 2n plus 1 plus 1, okay? And then the negative 1 to the nth here we can ignore because we're dealing with an absolute value sign. And then in the denominator, we're going to have the a sub nth term, which is x to the 2n plus 1. Okay. And again, we're gonna check if that limit is true. So let's work out some details here. This is the limit as n approaches infinity. And I misspoke earlier. The top power is going to be 2n plus 2 plus 1. So that's going to be x to the 2n plus 3 over x to the 2n plus 1. Okay. And so this is going to turn out to be the limit as n approaches infinity of x to the third over x to the first, which is going to turn out to be, and now the n's are gone here, so this is just the absolute value of x squared. Okay? So we know that the series will converge for values of the absolute value of x squared is strictly less than 1. So take the square root, and we can basically say that it will definitely converge for x between -1 and +1 with these strict inequalities. Okay, that's the great thing about the ratio test. We can find a range of where the series will converge. But one of the things that the ratio test does not tell us is what happens if this limit is equal to 1. Right, that we do not know, right? So one of the things that we have to do is test the boundaries. And again, the ratio test doesn't tell us whether this is an equal sign down here or not. So what we need to do is we need to test the boundary values. If x is equal to 1, right, let's see what series we get here. Well, if x is equal to 1, you plug 1 into here, you get 1 minus 1/3 plus 1/5 minus 1/7. Right, so the series becomes 1 minus 1/3 plus 1/5 minus 1/7, okay, plus 1/9, and so on. And we can see that this will converge by the alternating series test. Okay. So this is good. When x is equal to 1, we will have convergence. Next, let's check the other boundary. What if x is equal to -1? Well, if we take -1 and we put in for this value, you're going to have -1 plus 1/3 minus 1/5. Plus 1/7. So basically the negative version of this. So this also converges by the alternating series test, same as above. And since it converges at the endpoints, we can add these equal signs in here, that this power series will converge when we use it to approximate tan inverse of x for any value of x between and including -1 and +1. So that was a great, an intense example. But the main idea to take away here is that we could use power series expansions to approximate and represent transcendental functions, functions that may otherwise be extremely difficult to figure out. All right, so we'll end this video here. We'll look at some more examples and details in the next one. As always, keep working hard. Thank you for watching, and have a wonderful day.